Good afternoon, everyone, and thank you for joining. Today, as was mentioned, we're going to be discussing practical pharmacy upgrades, and I'm going to be providing a brief update on the USP guidelines. So there are three keys to success for pharmacy upgrades. The first is understanding USP requirements. Second is meeting owner needs. And the third is working with existing or new infrastructure capabilities. The first key to success is understanding the USP general chapters 795, 797, 800, and 825. These four chapters have gone through major changes over the last couple of years. And these changes include architectural finishes, programming, and MEP systems. These guides were first published on June 1st, 2019, and were slated to be officially adopted on December 1st of 2019. However, several appeals were filed that have postponed the adoption of 795, 797, and 825. The appeals for 825 were rejected, and so now it is slated to be adopted December 1st of this year. However, 825 will be informational until 795 and 797 have been adopted. However, it is highly recommended that the information contained in the guide be followed. Therefore, the current official versions of 795 are 2014, of 797 is 2008, and as previously mentioned, 825 will become official as of December 1st of this year. However, the previously publicized version should still be used for the design of all new pharmacy spaces. The appeals are for BUD only, which is the beyond use date for the compounding chemicals only, and do not impact the architectural or MEP requirements. As a part of the revised guidelines, very specific requirements were put on where compounding can occur and specific pressurization requirements within the pharmacy spaces. The intent is to ensure that airflow paths move from clean to dirty spaces so that your direct compounding areas are your cleanest spaces and your general pharmacy work areas are your dirty spaces. The ISO Class 7 spaces require 30 air changes, and the ISO Class 8 spaces require 20 air changes. These ISO spaces are generally known as your clean rooms, where the unclassified SCAs are your general work areas. This is a typical general pharmacy layout that shows the airflow movement in accordance with the USP general chapters. The pharmacy work area is considered your dirty area. The anteroom is one of the most critical spaces in the whole operation of a pharmacy. Not only is this used for pressure control and maintaining the pressure relationships between the different space types, it's used by the pharmacist for garbing, staging, as well as hand washing. As the pharmacist moves from the pharmacy work area into the anteroom, they've encountered their first clean space. This space is positively pressurized to the work area to keep contaminants out. Just north of the anteroom is a non-hazardous buffer space. This space is ISO Class 7 as well. And compounding is completed in a biosafety cabinet or a laminar airflow style workbench. This space is positively pressured to the anteroom. South of the anteroom is a hazardous buffer area. This area is ISO Class 7 as well. And work is performed in a biosafety cabinet or a CACI. And this is exhausted to the outdoors. This space is negatively pressurized to the anteroom to ensure a safe working place for the pharmacist. Compliance with USP provides not only safe drugs, but a safe working environment. The second key component for a pharmacy is understanding owner needs. The first of these is flexibility. Can or will space classifications change during the life of the pharmacy? What are future program requirements for the healthcare facility? Will the space be expanded? We recently worked on a project where the original programming called for a storage space. However, the facility was undergoing a major expansion with the increase of hospital beds, and it was quickly determined that they were going to need future compounding space. So while the initial programming was for storage, the space was designed to be able to support a compounding in the space in the future with minor changes. Designing for flexibility in the future will avoid whole room upgrades due to out-of-date or below classified equipment. Rooms can also be designed with full ISO 7 classification with Class 2 BSCs, even when using the room for non-hazardous applications. This also allows for flexibility to upgrade the room or if USP regulations become more stringent in the future. Maintenance is critical for pharmacy spaces, and it's important to try and minimize complications of performing maintenance within a pharmacy. In new pharmacies, structural ceilings can be utilized in conjunction with light fixtures that are accessible from above to allow for maintenance personnel to perform maintenance from outside the pharmacy envelope. Go back a slide, please. All valves can be located above a corridor ceiling to prevent the need to access them from within the pharmacy space. And piping should be kept out of the ceiling space above sterile areas to prevent the possibility of leakage into the sterile space. HEPA filter testing ports can be piped outside of the pharmacy space so that periodic testing may be done without entering the pharmacy itself. By incorporating some or all of these compact concepts, the impact of routine maintenance on the day-to-day operations of the pharmacy can be minimized. Reliability is also critical. Redundant HVAC units can be provided to ensure that required air changes and pressurization are maintained during periods of maintenance or unit failure. This can be accomplished also through multiple fans and multiple cooling coils, or in the case of DX system, refrigerant circuits can be used to ensure that temperature and humidity control can be maintained out throughout the life of the project. Pharmacy designs for new building offer the opportunity to design systems with the most flexibility. New equipment can be optimized for a facility's long-term needs. There are higher initial costs, but lower potential life cycle costs through reduced energy, reduced maintenance, reduced downtime, and designing for potential future upgrades. Most pharmacies, however, will be upgraded. Most pharmacies will be existing, however, and will be upgraded to meet the new USPs. The methods for dealing with this type of upgrade are to either incorporate areas around the existing pharmacy into the new pharmacy footprint, or construct a new pharmacy in an alternate location to ensure the existing pharmacy remains operational at all times. Both options are restricted by the amount of available space within the existing hospital, and the decision between the two is typically driven by where and what space is available. Another major hurdle to existing pharmacy renovation is the capacity of the existing equipment. If the equipment was designed for use in a non-pharmacy space, the air handler, fans, and electrical infrastructure may not be able to convert to the higher required demand. Air handlers not designed for HEPA filters may be undersized for pharmacy applications due to the additional static pressure added by the filters themselves. In these situations, it is possible to include fan filter units to provide filtration and increase air changes to meet USP requirements. Additionally, it's important to understand that pharmacists wear multiple layers of protective equipment. Therefore, it is important to understand the system's cooling capabilities. Compounding areas can have high density heating loads that can be difficult to maintain a space temp of 65 or 60 to 67 degrees in. Additionally, humidity control is required for USP. This graphic shows a typical layout for a new HVAC system used to comply with the USP guidelines. In this system configuration, the air handler component contains most of the major components. A HEPA filter would be located in the air handler to provide the HEPA filtered supply air. A fan array or multiple fans would be provided to provide the increase in static pressure needed, as well as the reliability and redundancy. Cooling and heating coils would be sized to meet the demands of the space. And in this configuration, supply air is supplied to each individual space through a distributed system using terminal units. The air is distributed from laminar flow devices located at the ceiling. Using the anteroom as an example, return air travels back to the unit through low return air grills. This is true for the anteroom as well as non-hazardous compounding rooms. In the hazardous compounding room, both the hood as well as the room exhaust air are removed from the space through a dedicated exhaust system. In this example, the air handler meets all of the air change requirements, the HEPA filtration requirements, as well as providing temperature and humidity control. This system shows what would be required typically to meet a renovated HVAC pharmacy. In this diagram, the existing air handler would have been designed for a non-pharmacy space. And in order to comply with USP, HEPA filtration and air change requirements would need to be provided for the space, but most likely would not be able to be accommodated by the existing air handler unit. To meet the requirements, fan filter units are provided. The distribution is very similar, except for supply air being ducted directly to the space. They're ducted to the return side of a fan filter unit. A fan filter unit is nothing more than its name implies, but it's a fan, a HEPA filter, and a laminar flow air device. The key to this system's operation is the fan filter unit's fan provides the additional static pressure required to overcome the pressure drop of the HEPA filter. Additionally, instead of all the return air being recirculated back to the air handling unit, a low return is supplied to the space, which can return air directly back to the fan filter unit. This allows for the equipment to meet the air change requirements. In this system configuration, the air handling unit is only responsible for meeting the cooling, heating, and humidity control needs. The fan filter units supply the HEPA filtered air and meet the air change requirements. To meet air temperature and humidity requirements, the AHU cooling coils must be sized to meet a discharge air temperature of 48 to 50 degrees Fahrenheit. Typically, chilled water systems cannot maintain this leaving air temperature. Therefore, direct expansion coils and condensing units are often seen for these types of air handlers. The DX coils are more than capable of meeting 48-degree discharge air temperature, if not lower. It's a good idea to have partial redundant cooling via multiple coils, or if DX coils are used, a minimum of 2 individual refrigerant circuits. This will allow for the unit to still provide some cooling to the space if one of the coils or refrigerant circuits were to fail. Fan arrays can provide increased redundancy and reliability if additional static pressure is required, as these can easily be retrofitted into existing units. Placing UV lights located on the discharge face of the cooling coil will provide control of microbial buildup and contamination in the airstream. This is commonly provided to ensure pure air is delivered to the space. However, with the current pandemic, they're more and more common as to provide healthy, clean air to the general areas as well. The two biggest challenges when it comes to providing lighting within pharmacies are limited ceiling space and lack of natural light. Ceiling space is at a premium within pharmacies, and once all of the HVAC equipment has been accounted for, there isn't much space left for other trades. This requires light fixtures within compounding areas of the pharmacy to occupy the minimum amount of ceiling space while maintaining a high foot candle level of roughly around 100 foot candles at the work surface for precision tasks. The traditional method for lighting these spaces is to provide IP-rated, recessed, linear style light fixtures within the compounding rooms. When space is more at a premium, an alternate method of lighting the room has recently been implemented, which is to combine the fan filter unit and a lighting fixture into one simple package. With this new technology, there are various styles. Some include a diffuser with thin linear recessed LEDs around the perimeter of the fan filter unit, or a diffuser with a perforated lens that refracts perimeter mounted LEDs to create a fully illuminated lens, similar to that of a standard LED fixture. Both concepts help to provide the recommended lighting levels within the compounding pharmacy space, while also reducing the amount of equipment located within the ceiling. The second challenge involves providing appropriate lighting within the overall pharmacy area to maintain a high level of productivity. There is typically a lack of natural daylight within the overall pharmacy, as most are located at the heart of the hospital with no exterior windows. Light fixtures within pharmacy areas are typically provided with blue-rich color temperature in the 4,000 to 5,000 K range, as these have been found to increase productivity. Further studies, however, found that this blue-rich light is detrimental to night shift workers as it interferes with their natural circadian rhythm. Most pharmacies typically operate 24/7 along with the rest of the hospital, so it's important to factor in the effects of these light fixtures will have on the health of both day and night shift employees. In order to minimize the negative health effects of the lighting, circadian rhythm lighting controllers can be provided to increase the amount of blue-rich light during the daytime hours and reduce it again during the nighttime hours. This will help keep employees at their peak productivity throughout the full day while mitigating any negative effects caused by the light fixtures themselves. While these types of fixtures and their associated controls typically come with higher upfront costs, the increase in productivity and well-being of the pharmacy employees have the potential to lead to higher return on investment when compared to standard LED light fixtures. While it is not code required, we highly recommend that emergency power be included as part of the design whenever possible. Compounding rooms become subject to recertification whenever the airflow or air change requirement or the temperature and humidity requirements fall outside of the desired levels, and this can easily occur if there's loss of power for a short duration. Additionally, product is put at risk of expiring due to loss of refrigeration equipment. Emergency power can greatly minimize the risk of lost revenue associated with both lost production and pharmacy downtime. The goal of the USP standards are to provide undamaged drugs to patients while keeping the pharmacist safe during the compounding process. Ensuring the compounds are not contaminated by any outside sources is imperative to maintain their purity and effectiveness. Infrastructure is the first consideration when determining the cost, overall scope of work, and system types. If existing infrastructure for the building is built for another application or is at its maximum capacity, the ability to install a new pharmacy area can be very challenging. This can lead to higher upfront costs and increased coordination for the construction team. For projects where all of the infrastructure is expected to be new, some of the costs can be minimized for future projects by providing infrastructure that is flexible enough to meet most pharmaceutical needs. The most common designs will involve upgrading existing pharmacies to bringing them up to the requirements of the new USPs. These designs will inherently involve the most challenges, as typically the existing pharmacy will need to remain operational while the upgrades are made. These types of designs will typically have higher coordination costs associated with them. Thank you.
Thank you, Seth. I do have a question, a couple questions. I understand that the state of Connecticut biosafety hood exhaust needs to be on a separate exhaust fan system from general/room exhaust in the hazardous compounding room. Do you see this additional requirement in other states?
Yes, this requirement I have found to be pretty much nationwide. And in addition to that requirement, there needs to be redundant fans for that exhaust system. So yes, that's pretty much a universal requirement.
Thank you. Another question is, what is the biggest challenge you have had with a pharmacy renovation and how did you handle it?
A recent project we had, we knew at the very beginning of the project that the owner had operational issues with the air handler. However, they really didn't have the budget for replacing the air handler. So we had to get really creative and really dig deep into what was going on with the system and what was currently there. It was an older system. The system was designed in such a way that the air handler was supplying all of the air change rates needed for the existing